we do the numerical problems of chapter number 10. This is chapter number 7 of my personal book. So let us do example number 7.1. The time varying magnetic flux in the vicinity of a conductor is 5 into cos of 100 pi t milliweber. Find the voltage which is induced across this conductor at time t is equal to 1 millisecond. So in this numerical example, a conductor is placed in a time varying magnetic flux. Voltage will be induced across this conductor. We need to find out the equation, the instantaneous equation for the voltage which is induced across this conductor, and then we need to find out this voltage at time t is equal to 1 millisecond. So the magnetic flux is a time varying magnetic flux. Definitely the voltage across this conductor will be equal to minus d phi by dt. So we differentiate the time varying magnetic flux with respect to time. If we differentiate the time varying magnetic flux with respect to time, we obtain 5 into 100 pi into 10 raised to power minus 3 sine of 100 pi t. We simplify the right hand side of this equation, and the instantaneous equation for this voltage is 1.57 into sine of 100 pi t. So this is the time varying voltage that is induced across the conductor. We need to put the value of t on the right hand side of this equation, and you know that t is 10 raised to power minus 3. So the time is 10 raised to power minus 3. If we put the value of t on the right hand side of this equation, we obtain the voltage across this conductor, which is 8.22 millivolt. So the answer of this question is 8.22 millivolt. We do example number 7.2. In example number 7.2, the electric field intensity is given. This is the equation for the electric field intensity, which is 8 into sine of 6283 t plus 6z ax volt per meter. Find minus curly b by curly t. So we need to find out minus curly b by curly t. So what we do over here, we consider one of the 4 equations of Maxwell's. This is one of the 4 equations of Maxwell. This equation of Maxwell says that a time varying magnetic flux can generate a time varying electric field. So the curl of the electric field intensity in this equation is equal to minus curly b by curly t. So if we want to calculate minus curly B by curly T, we need to calculate the curl of the electric field intensity. As the electric field intensity is in the rectangular coordinate system, so we calculate minus curly B by curly T in the rectangular coordinate system. So this minus curly B by curly T is basically equal to del cross E. And we calculate del cross E with the help of this determinant. In the first row of this determinant, we have the unit vector AX, the unit vector AY, the unit vector AZ. In the second row of this determinant, we have curly by curly X, curly by curly Y, and curly by curly Z. While in the third row of this determinant, we consider the X component of vector E, the Y component of vector E, and the Z component of vector E. Let us consider the equation for the electric field intensity. So here is the equation for the electric field intensity, and you see the electric field intensity is in the direction of the unit vector AX. This means that electric field intensity has got one component only, which is the X component. The Y component of the electric field intensity is 0. The Z component of the electric field intensity is 0 as well. So there is only one component of the electric field intensity, and there is the X component. The Y component is 0 and the Z component is 0 as well. So we put the X component of the electric field intensity in this determinant. The Y component is 0 and the Z component is 0 as well. If we expand this determinant, we get del cross E, which is basically equal to minus curly B by curly T in accordance with one of the four equations of Maxwell. And minus curly B by curly T is equal to 48 into cos of 6283T plus 6Z into AY. So this is the electric field intensity. This is the value of minus curly B by curly T in this numerical example, and this is the answer of example number 7.2. We do example number 7.3. Let us do example number 7.3. Well, the sliding conductor in figure number 7.2 is moving with the 16 meter per second. I'm sorry, I don't have figure number 7.2 in this numerical example. I have already explained figure number 7.2 in the theory of chapter number 10. So for this numerical example, you guys will have to consider figure number 7.2. So the sliding conductor in figure number 7.2 is moving with 16 meter per second. So the velocity of the sliding conductor is given to you guys, which is 16 meter per second. In magnetic flux density of 4 millitesla, you see the magnetic flux density is constant with respect to time. The magnetic field, the strength of the magnetic field is not varying with respect to time. So there is a conductor which is moving in this constant magnetic field, and the velocity of this conductor is 16 meter per second. Find the reading of the voltmeter if the length of the conductor is 0.2 millimeter. So we want to find out the voltage which is induced across this sliding conductor. The voltage which is induced across the sliding conductor is read by the voltmeter in figure number 7.2. I don't have the figure over here. Anyhow, you guys can consider this figure in the theory. So we calculate the voltage or the reading of the voltmeter with the help of this particular equation, which is minus B Vd. Minus B is the magnetic flux density, which is given in this numerical example. There is 4 millitesla. V is the velocity of the sliding conductor, which is 16 meter per second. D is the length of this sliding conductor, which is 0.2. So we put the values on the right hand side of this equation. You see the magnetic flux density is 4 into 10 raised to power minus 3. The velocity of the sliding conductor is 16 meter per second, and the length of the conductor is 0.2 meter. So the reading of the voltmeter will be minus 12.8 millivolt. This is the reading of the voltmeter in example number 7.3, which is minus 12.8 millivolt. We do the last numerical example of chapter number 10. There is example number 7.4. So let us do example number 7.4. The equation for the magnetic field intensity is given in example number 4, which is 4 into sine of 6283t plus 2z into AX ampere per meter. Find the amplitude of the displacement current density if the conductivity is 0. So the conductivity of the medium is 0, and we need to find out the displacement current density. So the displacement current density is basically equal to curly D by curly T. We need to find out curly D by curly T in this numerical example. So we recall one of the 4 equations of Maxwell. This is one of the 4 equations of Maxwell. We recall one of the 4 equations of Maxwell. The curl of the magnetic field intensity is equal to J plus curly D by curly T. J is the conduction current density, which is the current per unit area, and curly D by curly T is known as displacement current density, and we need to find out this curly D by curly T in this numerical example. So we know that J is basically equal to sigma, which is the conductivity multiplied by the electric field intensity. So we replace J in this equation by sigma E. And we know that sigma is basically equal to 0. The conductivity in this numerical example is 0. So if the conductivity is 0, we obtain this particular equation. The curl of the magnetic field intensity will be equal to the displacement current density. So we can calculate the displacement current density with the help of the curl of the magnetic field intensity. So let us calculate the curl of the magnetic field intensity, and as the magnetic field intensity is in the rectangular coordinate system, we consider the curl of the magnetic field intensity in rectangular coordinate system. And the curl of the magnetic field intensity will be equal to the displacement current density, which is curly D by curly T. So we consider this determinant. In the first row of this determinant, we have the unit vector Ax, the unit vector Ay, and the unit vector Az. In the second row of this determinant, we have curly by curly x, curly by curly y, and curly by curly z. In the third row of this determinant, we have the x component of the magnetic field intensity, the y component of the magnetic field intensity, and the z component of the magnetic field intensity. If you look at the equation for the magnetic field intensity in the previous page, here is the equation for the magnetic field intensity, and you see the magnetic field intensity is in the direction of the unit vector Ax. This means that the magnetic field intensity has got only one component, which is the x component. The y component of the magnetic field intensity is 0, and the z component of the magnetic field intensity is 0. So you see, here is the x component of the magnetic field intensity, which is 4 into sine of 6283t plus 2z. The y component of the magnetic field intensity is 0, and the z component of the magnetic field intensity is 0. So we expand this determinant, and the expansion of this determinant gives you the displacement current density, which is curly D by curly T. So curly D by curly T is the displacement current density, and the displacement current density in this numerical example is equal to 8 into cos of 6283t plus 2z Ay. We know that the unit of the displacement current density is ampere per square meter.